We're not going to talk about acceleration anymore.
I was thinking about something completely unrelated.
I'm going to be recorded. I'll find out later.
Oh.
All right. So
I
the
got
moving
the
egg,
guy, Ben.
okay, the egg had a physical quantity that we haven't really discussed this year yet, but you guys have used the term, I know. Right. The egg had momentum. Okay. Because it was moving, it had this quantity known as momentum. Okay. Now, sometimes people think that it's the same as inertia, but inertia, remember, something has inertia because it has mass. So this is a kilogram, and so its inertia is described as that of a kilogram. If the kilogram is moving, now it has momentum. Okay, so it still has the inertia it had, but it has momentum now because it's moving. So if this 1 kilogram is moving at 5 meters per second, and then it's also moving at 10 meters per second, it has more momentum when it's moving at 10 meters per second. But it still has the same inertia the whole time. Okay, it has inertia described as 1 kilogram. However, its momentum is different because of the change of its velocity. So momentum, the quantity momentum, is given the variable lowercase p. Okay, that's momentum, not m. M is mass. P is for momentum, and momentum. An object has momentum when it has mass and velocity. So m times v, the product of m times v is the momentum of an object. So the faster it's going, the more momentum something has, the more massive it's going, the more momentum it'll have if it's moving. And the units on momentum, well, the units on mass are kilograms, and the units on velocity are meters per second. So that's the unit. The kilogram meter per second is going to be the unit on momentum. Okay, so there is somebody throwing the egg. All right. One time they're throwing the egg into the wall, the next time they're throwing it into the sheet. Okay. Now, let's try to put some numbers to this stuff. So, we'll give the egg a mass of 1 kilogram. That's a little bit much for an egg, but it'll work. And let's say that in both cases, the person throwing the egg releases it, and it has an initial velocity of 5 meters per second. Okay, so that is the mass and the velocity of the egg when they're released. What is the initial momentum of the egg? 5, right? So the PI, or the initial momentum, is 5 kilogram meters per second. And the same thing in this situation, 5 kilogram meters per second. Okay, and now that egg has momentum. Think of that as something that it has. It's going to travel through the air in possession of 5 kilogram meters per second of momentum. So when it's mid-flight, it has PI, or not PI anymore, but a momentum. It has the momentum it began with of 5 kilogram meters per second. And that momentum is not going to change unless we do something to change it. It's just going to continue in motion with the momentum it had when it left the person's hand. And then it's going to come and it's going to hit this wall. Okay, so in this case, the egg is going to hit the wall. And in this case, the egg is going to make contact with the sheet, which is kind of going to stretch a little bit. It makes contact with the sheet. What is the final velocity of the egg in this scenario? 0. Right? And the mass is still 1 kilogram. It may be splattered, but it's still total has a mass of 1 kilogram. It hits the sheet, and the sheet is going to bring it to rest. So the final velocity of the egg in this case is 0. And still has a mass of 1 kilogram. So the final momentum of the egg in both cases is what? 0, right? The final momentum, PF, which would be mass times VF, is 0. So in both cases, we took this 5 kilogram meters per second of momentum away from the egg. How did we take it away? What took it away in this case? The wall, in this case. Both of them did what to the egg? Applied what? Force, right? Both of them applied a force. In the case of a wall, we know that the force would be enough to break the egg. So the force there, okay, breaks the egg. The force here does not break the egg. However, they both apply a force. Good? Everybody go with what I drew?
Yeah, I'm still drawing something quick.
I'm not good with that. Why not?
It was the same thing.
Something different happened, right? One case the egg broke, one case it didn't. What should be different on this? Yep.
Time it took for it to accelerate to a stop.
Well, I'm not showing time, right?
Force of the sheet should be smaller.
Right. This force should be less. So let's make it like that by doing this. This is a bigger force, right? Enough force to break the egg. This force is less than that. That is more accurate of what we want. Now, prior to today, you would say this egg had a greater acceleration, therefore we know because it had a greater net force. We don't want to talk like that anymore. What we want to say is that this egg broke, but for different reasons. I'm going to get to why. Which egg had a greater change in momentum? The top one? I'm getting this from somebody. What does that mean?
Neither.
Neither, right? They're the same. What is the change in momentum in both cases? Let's look. Momentum change, delta P, would be final momentum minus initial momentum. The final momentum was 0. The initial was 5. So in both cases, it was -5. Right? Change in momentum went from 5 to 0. 5 to 0. So that's a negative change, right? We're taking away 5 kilogram meters per second of momentum. So they both have an equal momentum change. Now let's look at something else. There's Newton's second law, F equals ma. Now we don't want to talk about acceleration anymore, so let's look at acceleration in terms of what it is, which is a change in velocity with time. And I'm going to take, basically we're going to combine the kinematics with Newton's second law. And we got F equals m Vf minus Vi over time. And then I got mvf minus mvi over time. One more step. I'm going to do this. F delta t is mvf minus mvi. And we're going to just end with that there. So the right side of the equation is what? The change in momentum, right? The right side of this equation is the change in momentum. And now the left side is something else. It's this relationship of force and time. The left side is going to be a quantity we call impulse.
What's that mean?
What's that?
What's that mean?
Huh? I'll tell you. You may be right. So looking at the wall situation, we know that we had a big F, and in the sheet situation we had a little f. Tell me about the time. How they compare? Top one has a small time, bigger time, right? Small time, big force, small force. Change in momentum is the same, we just get there differently. The Ft is the impulse, right? Impulse equals change in momentum. So this is the impulse that gives us our change in momentum. That is the change in our momentum. All right, I'm going to give you a couple. Now we said that the units are, on the left side, are the Newton per second. And you guys know that a Newton is a kilogram meter per second squared times, and then times a second. So the seconds cancel there, and so you see the left side actually has the same unit as the right side, right? It's the same units. Kilogram meter per second. Okay, which, the wall or the sheet, which one gives a greater impulse to the egg? Same, correct? Good job. Usually people say the wall. So that's a good thing, you followed well. What was greater for the wall? Force, right? But the time was less. So really, if this arrow represents the impulse, right, it needs to be the same length as this arrow. They need to be equal length. It's just how we got there was different. Small f, big T, big F, little t. Same impulse, because when I say the word impulse, you should think change in momentum. It's like, it's the same thing, right?